time to continue. Welcome back to my project of building a display and the CPU, and then let the CPU draw a line on that display using the Bresenham algorithm, and that within 24 hours. Okay, let's not hope that the whole thing will take that long, but well, we are already at 4 hours and 40 minutes, so yeah, it's time to come to an end. So yeah, this is already the PC which I designed in last part, and that needs to be connected to this and to a non-existing ROM. The problem is that ROM, so yeah, and there's another problem, and that is that that this is on this side, but that's an easy fix. I can just take this and say cut and flip it and paste it, and there we go. So now this is on the other side, and the LSB, the lowest significant bit, is on this side over here, so closer to here. And since I want to copy paste this decoder, the LSB is also on this side. This matches now. I don't have to flip that one then. This will straightforward, not straight, I should stop using straightforward. This will directly be connected to the decoder once I copied it over here. These 4 lines will directly be connected to these 4 here. There will be a little bit of space in between here, which is kind of non-aesthetic, but if there's enough space here, it's actually possible to put the 4 bits for the display in there. Let's just put them here. I need some color for the display bits, and once I have them, okay, this is the color. Once I have them, I can put the PC right next to it, so that the decoder will be here, and then we have the spacing done. So I said 4 bits, but we could use a different setup, but this is just the most easiest, and I don't want to put that much work into that part. This part, them part, their part. And this, I'm just gonna copy, and the question is how much space do I need from here? Let's assume that this row here is filled with repeaters, and because there's repeaters over there, so the first line or the first data can actually be at this position, and that means that there will here be the first bit, which is something like this. On the other hand, that means I have to see how this works. So basically there's like a repeater. That doesn't matter because repeaters they can just be like here at this point. That means that the decoder will be aligned. I'm gonna just copy the start of it over. That makes it very easy to actually no, I should stop using actually that intensively. I just copy it over. At least I'm not swearing as much as in the beginning of this video. Plus point, I hope. That will be here, so that tells us where to put the broken counter, which is, if we assume this our output, it should be somewhere here. So if I copy this, go here and say copy, I'll actually have it. I can just put that here. Like so. There we go. So this would be the decoder of the ROM. This is the broken counter. This is gonna be connected to there, and yeah, this is actually quite big. And it would be nicer if the broken counter would be here, and these bits on the other side of it. And I think I'm gonna go for that, because it's much more pretty. So we're gonna do the same game again. We got some wires here, and this is gonna be a repeater. Here we got the first bit of that. This is the first here. So I'm just gonna take whoopsie doopsie this, put here one, and then copy from here and hope the best. Cell B cut, paste. That looks good. Yeah, here's these are connected like really closely, so that should be enough space to play with it. Why? We don't read on the server. Yeah, this can be go again. Okay, and the thing is, we can just put like another one of these on that side. Means there can be like bits here, which then go to here. Oh, we could even put them below here, but that's kind of difficult to actually set the bits for it then. The only downside of having the decoder somewhere in the middle or even on top of the ROM is that it's kind of difficult to actually find the matching lines. You always have to fly over it instead of just staying in the line and placing the torches. So that's kind of something one has to be careful of. But yeah, that's basically the final placement of this thing. So my suggestion would be to put these violet or magenta lines to this and then just put them up with slabs and get them there, and that won't gonna be the one on this side. Okay, so that will be the LSB on this side, the lowest one, which will be on this side, which is kind of annoying because we got the LSB here on the other side. One has to always watch out where the LSB is actually where the MSB is, and not mess that up. And trust me, one easily messes that up. But I believe we're gonna use a text editor anyway to place the bits. For simplicity reason. By the way, text editor, it's required that we have a distance here which actually matches this setup, which is the case. So, which is not the case. Damn it. Okay, that's not good. But I assume that, considering that here will be the last way which actually powers this, and we need like that many outputs, we can hope that it reaches all the way here, and it does. So this torch is able to deliver up to this point, means that we don't need that repeater here, and we can put a signal below here. Nice. These can be gone, they are not needed, they're just were for measurements. So yeah, that's the 4 bits for the display, and yeah, cool. So this works smoothly. Water. Now comes the easy part, wires. And the most annoying part. Oh no, I can use this because reasons. Obvious reasons. There we go. That was the first one. Now the second one. There we go. Next one. Dun, 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 dun. What fillet later do, Jandalando, Jilano, fillet later do, all of it, Haley. What fillet later do, Jandalano, Shilano, fillet later do, Fia Haley. Okay, okay, okay. Considering bananas, and that should be a slab. Bum, 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 bum. Is it? No. No, it's not. Oops. 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 There we go. So that's the wires. That's actually not helpful. Oh gosh, I haven't placed any of the repeaters yet. That's gonna be an annoying task. There we go. So that's wired up. That comes last. I'll need a bunch of more wires here, and yeah. So that's the absolute jump address. The jump address in summary. That's where we jump to. That will just be delayed, like forwarded up to this point. An actual, oh, stop that word. Since I am aware that I'm gonna, not aware, that since I know already that I'm gonna put repeaters in that row, I can already put the colors and blocks down and place repeaters all at these points, and ba-ba-bum. Now I need some repeater again. Here's one. Okay, so something like this. That also means I'm actually able to put the stuff there. Okay, this is on, so perfect. Signal strength is plenty. Boom, I need this. The nice thing about this kind of CPU is that you normally don't need much timing, because this is a really simple and basic CPU. It has just one critical point, and that is when you, at the end of the cycle, save everything. Saving everything be like you trigger this line here once, like so. Saved. That's the point where it will save whatever is on top of here with whatever selected line. Same happens here. The point of saving is actually when we trigger this block or that one. So yeah. I think it's time to like put a lot of repeaters into the whole CPU, and then actually, or maybe not yet, but at some point. Thing is, I need to connect these here, and that's kind of a tricky thing to do, because that needs to be connected to the CPU and or either. So basically, depending on whether these three lines are on, it's we power this or this one, not both. So yeah, I think I can use comparators for that. I haven't used any comparators in this, and they're such good AND gates. Or I don't know. But I should connect this first, because else inconsistency. Like then I can say, hey, PC is done, and then I say I do SS stuff. It's just more sorted. Problem is I need some block. This one, and done with you. Good. Or not. I think I need, yeah, I need, wait, this is already inverted, so I can go here and just connect this like so. I can put like a torch here, and oh no, not a torch, a repeater here, but that's not going in there, so that's no go. I can do this, repeat it to this, and torch in the other direction, right? Like so. The problem is, doing like this, I cannot cut off this signal, which is kind of not what I want, so this is not the prettiest solution I can do. What other solution may there be? Oh right, oh I totally forget this. Thing is, this is gonna be a pulse, like this black wire is always a pulse. So what can I can just remove this and put something like this here. And now is the point where I get my comparator in this, because that comparator blocks the signal which we want to send there. Let's just go below here, and for the sake of it, yeah. On the other side, we're gonna do the same thing over here, just at a different position. Maybe it's possible to do this. Point is that I need a torch here. Okay, there we go. Now it's unset. And all are on because of this. There we go. So, okay, this would do the job. Like, we send a pulse in this, and then the pulse goes there, and goes there. The only problem is that these things, torches and comparators, don't like one-tick pulses. So, the point which I need to check here is, does this work? Sending one-tick pulses through there, it may work, it may not work. If you follow redstone by the guidebook, it should not work. But who knows? And as you can see, it's not working. This one is flashing, but this one is not, because it's not going past it. That means wasted effort. I have to put this back, apply that one again, put this one back, put that brown wool on top and over here, and so we can actually put that there on this type of block, because it's that. It's hard, it's rock hard. Problem is, does this work on this side? As you can see, no, the signal is not traveling through. Let's just try 2-tick-1. Yeah, that's all off, so that is totally natural. So I should try this one. Seems to work, right? So 2 ticks, no issue. So that one gonna be resetted with 2 ticks pulse length. There we go. And just because it's so nice, I just try it again. Perfect. Synchronized. Beautiful. Yeah. But I'm gonna put the what is it called? This thing here, because it's perfectly, whoops, it's perfectly possible to put this right next to it, like in this, and then power it like this. So if I do this, it works. I just need to swap the values for testing. and then there we go. I'll turn them off, and this one works too, of course. Perfect. Good. Now the tricky part is actually, not actually, stop that, is to use the blocking. I need a wire for that, from there to here. So let's find a wire in a nice color. Yellow. Okay. Server has given me yellow, so let's use it. As said previously, these are just connected. What we can do is, at this point, we can just connect this like so. So whenever this is on, that means that we will not use this one, but we're going to use this one. So what's possible to do is to put something like this here, and so, because then this is off, and that means this can travel to here without issues. On the other side of it, or for aesthetic reasons, I'm going to use this design. We can use this, but I need to put a repeater there to cut whatever signal strings come from here off, like so. Maybe I think that should do. Say side input is 15, perfect. Okay, so doing this, it should apply 0 to the output, which is exactly what it does. But not having these connected, which by the way all reach the destination, so I can remove these. If I do this, it will give us 1, which is that one, and that works perfect. So that's how we got the switching done. Kind of easy, perfectly matches actually. It's like perfect positioned opposite to this. I couldn't ask for more. Yeah, except a nice wire from here to that display, but yes, that's a different issue. So let's assume that this machine is now totally ready to jump. That's good. The whole PC is done. The only thing which is actually missing is the clock, which connects this one with this one, and yeah, that's it. But before that, we should add something like repeaters. As one can see, that's all disabled. The signals all reach until the designated place, so there's no use in changing the control bits. Going from here to the ALU, that's all perfect as is. It's different for the A decoder wires. They already stop halfway, and the main issue is that like they need to be enhanced, like extended on top of this here. One way to do this is to have, funny, we want to be this in sync, so these three need to receive the signal at the same time. One thing to do this is to put repeaters here at these positions. It's the same distance for all, means all receive the signal at the same time. Same goes for these, but at this point it stops. So that is where we're gonna put the next row of repeaters, and also connect them like so. Now this means that all the other ones are 1 tick later, but also in sync. That means whatever value we insert here, it will never activate the wrong one, it will always activate the right one and disable the other one, which used to be previously on, if any. Same thing gonna happen for this one here now. Basically, as you can see, this is also not really reaching here, so we need to have like somewhere some repeaters. That's not really important where, because we need one on top anyway. What's with this one? Oh, okay, I get it. So for aesthetic reasons, we're gonna put them all next to each other. There we go. That row is totally enabled. I'm gonna just have a look. It reaches until this point, so I'm gonna put them here. Blop, blop. I'm gonna put that banana peel away. It smells. Don't want to smell banana all the time. I mean, banana is nice and so, but don't give me that stench. Okay. That's the two easy ones. 7 should be on this side, this is 7, and here is 7 on this side. So 7 is always this one. Even on top of this, damn it. I'm talking about SS. There's like this little issue here, that this was not, that this one is kind of wrong. Where we have the LSB. LSB should be on this side. LSB means it's the one at the front. Where's this no repeater? There we go. And this has to be a repeater. So the rest is the repeaters, but we don't need repeaters there. For example, that one is a torch. That not. There's a torch. Oh, come on. And this is a torch. So this is not, because the 0 is not existing. And all the ones at the end are also torches, like so. Because that was 3 here, and then comes 4, and then 5, 6, 7. Perfect. So the torches are fixed on this side. I just never finished that. And 7 is also on this side, so this is always the register with number 7. Time to disable these. There we go. Yeah, in general the speed until the register is red is 2 ticks. Well, 3 if we count these, but since they're always the same, we don't count them. There may be difference if we have like a repeater here in between, then they are also offset, but it doesn't really matter, because that just means that the total cycle speed is in the worst case increased, but that's all. Funny and lucky, we have this here. Like, we can easily put repeaters in this without any big issue, and okay, this is stupid. Need a repeater. There we go. So like this, we're gonna extend it like that, and this one, meh. Okay, this one is kind of difficult. So what we're gonna do is quite simple. Just put that on top and put this one here and that one there, and then we're gonna put this one here, and that's it. Yay. Yeah, looks weird. Oh, for aesthetic reasons I'm gonna put that, but it's actually totally valid. And actually it looks better than before, because we got rid of this weird peak. Point is, it just takes 1-2 ticks until the signal here reached. Always. And that's not the case for like up to this point. So what we're gonna do is, even though this reaches further, I'm gonna put this here, so that all have the same timing of these. Perfect. So that's all the SS stuff for the reading part. There we go. Phew, Okay, there's one more. That one. And then we got all the SS lines fixed, actually. Oh, that's good. Except the yellow ones here, must not forget them. Okay, there we go. So 1, 2 ticks until it's on that line. And okay, that means that this one is settled. What we're gonna do now is we're just gonna crush that redstone to see where the repeaters have to be placed on this in the worst case. And that is somewhere here, directly under the torch. Awesome. There we go. And this reaches until the XNOR. Perfect. And for simplicity reasons, like so, we're just gonna put it there too. But I will test that it really works. Yep, works. It's not under a torch and it reaches. Perfect. Okay, and this also reaches the end. So do all others. No problem with this. Good. The register is fully empty. We got that settled. The only thing which is missing now is the ROM, the decoder, and the clock. So I would say clock first. How long am I recording? 30 minutes, and 30 minutes for setting up this stuff. Oh, that's okay. And all the SS things. Clock can be somewhere here on top. We're gonna find a way to put it neatly. Sexy. Not. Yep, something like this, and for testing purposes I'm gonna put a torch here, so this wire goes, yeah, that's fine. And so let's just say we're gonna power at this point. And this wire goes until here. Nice. But at this point is where I should put a piston to signal cut it. I don't want to like save for a whole half a cycle. So I'm gonna put this on top, and then it just signal cuts this. Whatever, 3 takes plenty. This is cut it here, so as you can see there's always a signal cutter in the clock. Well, has been going until you stopped me for answering. Yeah. Anyway, continue. So that is what happens if we finish a cycle. We're gonna just put stuff here. So the question is, how fast is this CPU, or in other words, how slow? there's no way to figure that out. Like I could like just put random repeaters here and just say yay, okay, cool, done. There it goes. 1, 2, not 2, 10, 11, 13, 14, whatever, 15, 0, and so this just loops, and this should be saving no register because none is used, so let's just put something like this here and a torch. And we can see that this one will constantly write because that is what happens at the end of the cycle. End of the cycle here, beginning of the cycle here, beginning of the cycle, we set the next number. And that is when the next instruction will automatically ripple into the CPU and cause things to happen. Exactly. So I should move this a bit more out of the way because I cannot move it more like that direction, and I cannot move it in that direction, and here should the ROM be, so this display is kind of in the way. I got plenty of space behind it though, so I'm just gonna move it there. Move whatever 20, just go out of the way. OMG lag. There we go, so nice. Point is, I'm gonna get that decoder now. Clear land 1 set. Oh no, okay, not gonna do that. She's gonna set here and here and here. Ugh. Oh no, don't do this. I hate that feature. And then copy. So I can just put it like here. There we go. There's no flickering, no nothing. It's just perfectly going 1 over. So a showcase. Let's not do this. As you can see, it's flickering. You can see how the lines before sometimes just flicker, and that's really nasty. Like, I mean, it doesn't matter because it's just a tick, but it's ugh. You know, you don't want that. In some cases, it may be really horrible to have that kind of effect, and right now it's just perfectly in sync. That means it's not flickering at all, it's just going 1 at a time. Not jumping right madman. And it's also a sign of quality if you have it perfectly like that. Less redstone updates too, by the way. Yeah. So the thing missing now is actually the ROM. Yeah. So this is kind of an issue. Let's see, I got this. ROM building is like a real complicated thing. It consists of that and done. Okay, that's maybe a bit much. Just do this with just 1/16, 16 lines of that. Perfect. Okay, the real difficult part is to put actually redstone on top, because you just keep forgetting. Set redstone test, was it? Yeah, that's the real difficult part. And tab completion doesn't even work if it's not wire. It's wire. I keep forgetting that. There we go. Perfect. There we go. ROM bottom half done. This is a bit more of a tricky thing here because I like to keep things separated. So each of the yeah, okay. section should have the same color as below, and the stuff in between should actually be barrier. Like in my case, I prefer to put barriers there because then it's like visible, you can look through it and it's more space, more roomy. So I'm just gonna remove these and replace the stuff in between with barrier. There we go. Perfect. So, time to put redstone on top. It's one of the 2 use cases I found for barriers. The other one is just to have nice lava behind the wall, see through. Okay, so time to put some of these here. I like to separate these in good groups, and so like that these sections are never intercepted, but in between sections it's okay. So we got this section which is program counter, but these have plenty of time. They are important at the end of a tick. Really, that doesn't really matter. These have time until all the reading is done. Before, these don't even need to arrive at the ALU. They have plenty of time. There's nothing to count there. This has time until the end of the cycle, like literally. So also no need to count that. I still haven't removed that block. Gosh, I saw the video of my recording and I saw how I did not remove that block and it triggered me. Oh good, now it's gone. Yeah. So counting this green thing is actually the last one to able to reach the ALU. It's nicer if these 2 go at the same time and reach there at the same time, because ICA is a little bit of tricky adder, because when the signal arrives in time, at the same time synchronized, these perfectly gonna retract and the signal runs through perfect in sync, no time loss, no anything. But if one is just a little bit later, then you may have the problem of one retracting and extending again, causing the time of the adder to be 1.5 ticks slower than original. So when you're using this and you don't have synced inputs, which is the case here, and I cannot sync these with this build because I would need to make all these the same speed. It actually works if you put the repeating exactly at the same position as the one in here, which is not the case right now. And here we got even the wrong direction, so that is why it's not possible to sync that one when you don't feed it from this side and have the same breaks, like the same repeating extensions, because only then you get the signal here at the same time and you have the right signal here. Another problem, we never have a time where there's no signal here. There will always be one register here, because we just have one of these clock things and that just changes the value here, so it will immediately jump from one register to another register without giving this RCA any break of extracting all the pistons. So there's no zero input, so this one will always be a mess, and you can always count this one and put 1.5 ticks on top as speed. So yeah, it makes it easier for us to actually put stuff data in there. On the other hand, this one is also totally desyncing the whole behavior, so just don't pay the mind and just count whatever needs to be counted. So that is time. This needs clock. Good. So let's start timing here. 1, 2, 3. Bullshit. 1, 2, 3, 4 ticks, 5 ticks, 7 ticks, 8 ticks, then we hear 8 ticks, and we need to go back here. That's 9 ticks. That is, well, let's just assume we got 9 ticks, 10 ticks, 11 ticks. This one is, assuming you got the worst possible condition, that is in the middle here. Where did I stop? 11, 12, 12 here, 13 here, 14 here, 15, 16, 17, 19, 20, 21, 22, till here, and that's where I'm quite unsure. I said plus 1 tick. 21, 22 was what I had, so let's just go 24 for security reasons. Then we go back 25, 26, and that's where we reach the point where we're gonna save 26. So the speed we need is about 26 ticks. 26 minus 2 is 24, and 24 by 2 is 12, and 12 by 4 is 3 of these. So this should be the whole CPU speed, if I'm not totally right or totally wrong and messed up the counting. Yeah, in most cases this would probably work with 26 cases. There may be some edge cases where it fails, but we're not going to use any of these, so we always get a little bit of buffer, and let's just accept it. It's always nicer if you have a CPU which is assumed that you input on this side, so that you don't have different lengths of cycles depending on which instruction you're executing right now. If you really do it properly, then you input the address in this side, so that it doesn't matter which you choose. Then you also have the same flow direction for the register decoder as the register, and you have it the ticks at the same position, same as there. It's the same for all memories. And some special injections will be injected right in time. The problem is I have to do that with this CPU at some point, because this is the synced ICA. It really is bitchy if you don't feed it at the right moment. It just doesn't work if you don't do that. You have to feed it properly. Everything in this thing has to be counted per tick. Every repeater has to be counted. And the signal has to be exactly where it needs to be. And that's also a reason why I'm not going forward with that one. But on the other side, you got real nice ICA, synced ICA, no piston, so no 0.5 takes. Real nice. Yeah. I think we got the clock done. Time to finish the memory. First of all, no. Never asked for that to be there. Stack 15. There we go. So this is our ROM. It's not fully done because of the reason that there's this thing. We need to put like a repeater there. Like here, and that reaches here, so perfect. I'm just gonna stack that one over. How many bits do we actually have in this? Oh, 4 plus 4 plus 4 plus 9 plus 4. 1, 2, 3, 4. 16 plus 9 is 25. Okay, so we're gonna do 24, and all repeaters should be placed. Perfect. So 25 bits is really horrible. Like, it's super awesome if you want to write code for this CPU, because you can do Fibonacci in 4 instructions with such a CPU type. It's not as easy with such a type, because here you can do normal operations and branching in the same operation, and that always, and that is awesome. You can make a normal operation and say, I just want to jump always after this instruction. I don't care, it's just a final loop. If you reach the last line, which may be this one, you can just say always jump to the start. I don't mind like what else I did in this operation. When I'm done, jump. And that is perfect, what you can do with this instruction, which really shrinks this the code. But it's also more annoying to debug. But that's, by the way, one use case of having this always jump, and that is, I believe, the case if you just put all of these on, because then no matter if the A is bigger or A is smaller or A is equal, it will always jump. Small question, why are there 2 of them on? Did I miss something in this movie? Why is that? Am I kind of failing my... Oh yeah, it's not subtraction. There we go. So if this is subtraction, then won't fail. So like this, and then we just go one of them. So perfect. If you want to always have this trigger, just put all of them on. It will always be the case. Either that one is 0, if it's not 0, whatever. I think there's one case where it will not be 0, and that is the case when you have this bit set and this here not. No, this also set. This also works. Damn it. Okay, maybe I have to do this. Okay, no, this has to be set. And this has to be set, else then these 2 are disabled, and then that one goes on. And if I have none of them, oh, then that one is on. Okay, so it's practically not possible to not have one of these trigger at a time. Means you can always have a hard-coded jump. And that is when you just put all of them on and put an address here. You will always jump, no matter what. If you arrive at that address, it's a jump. And that combined with other instruction really gets compact code. Yeah, we got it done. By the way, is this working? Is it actually jumping? We're there, so let's jump back by simply putting this here. It will always jump to 1. Always. Always means always, always. Always, even at that point. Problem with that is, oh, there's no problem. Like, this is a loop on the first line, and whenever we're here, we're gonna jump to 0 again. We're on 0, we're gonna jump to 0. It's easy. So yeah, we're at the point where we could, for example, try Fibonacci, just for testing this, or we directly hook this up to there and do stuff, but meh. Fibonacci is so easy. Okay, Fibonacci starts with numbers 0 and 1. So the first thing which we do is we're gonna write 0. We cannot write 0. Well, if we want to write 0, we just can do like, I need this here, my sword, a torch, and save that into, is that the LSB? It's the LSB. Okay, save that in address 1. So address 1 gonna contain 0. Then we do the next one with address 2. Address 2 gonna contain 1. 1 has to be injected via the immediate. The LSB is here at this point, because that was on the right side. That means we're saving 0 into 1 and 1 into 2 whenever we reach this point. Because I know that we can actually just put... great. Oh, I'm so good. I should stop putting blocks there. What am I doing? I don't want to jump to 15. Oh, no. Oh, damn it. Oh, here, come on. Just always jump to 0. Have fun. There we go. Go away. Stupid particles, go away. Thanks. So yeah, by now, did I actually save to? No, I saved to 1 and 2. So 1 and 2 should have a value. Since they don't have a value, that means I failed at some point in time. Now this is the important instruction. Let's just jump to let's always jump on this instruction, and always jump to, or actually always jump when I'm in this instruction, and always jump to instruction 2. Instruction 2 is that one. Oh, 1. This is actually the 1 instruction. So this will be stuck here and never change, as you can see. That means I can perfectly debug this instruction right now, because it's not working, and not working is always bad working. Boom. So there should be an output here, which is 1, perfect. 1 goes here, 1 goes to every of these positions. One of these should be on. It's that one, and it's saving. There's the 1. So is this getting unsaved? No, it's just saved all the time. Perfect. So yeah, it's perfectly saving. There's nothing wrong with it. Cool. I know that I'll have to jump back to the beginning of this instruction, so I'm just gonna put that here. Oh no, this is annoying. Really? If you place torches in here, it actually sucks so much. I need Sublime. Give me Sublime, cool, nice. And Minecraft. Actually, I'm gonna leave the full screen. Else I have the problem that like there's always it's going to desktop then always, and it's really annoying. And I need a terminal. There we go. Terminal is good. What we're gonna do is we're gonna go to desktop and create a new file, and that file gonna be, we'll go to desktop. I'm gonna write whatever, let's name it binary.txt. That's it. I now need a file which is probably located in my documents folder. Yeah, okay, like this, documents, and then Minecraft and compressor. Let's hope it's called compressor. Yeah, it's called compressor. Get that here. JJ compressor binary. There we go. It gives us this. This is a command called torture. A torture command basically takes all the binary which is in this file and converts it into a command. I can insert the command into there, and then we're done. So what we have to do is, at first, we're going to take all these 25 instructions and put them into the text file. But 1, 2, 3, 4, that's immediate. 1, 2, 3, that's that one. 1, 2, 3, that one. Down to 3, that one. 1, 2, 3. Wait. Okay, now I need I should put it like this, and now press that. Okay, there we go. So what I can do is I can write down EMM here and put this here, and this is actually A. Is it A? No, it's B. Then we got C, which is where we write to. The binary creation tool. Wait, is this still recording? Because my system froze. Okay, there we go. Yeah, it's not the most stable computer, but that's due to the system Ubuntu, I guess, I fear. Red goes to the upper one, and that is here, and that's A, thus. Then we got the next one, that's flags. So, the flags are actually, I'm gonna put them as single ones, because then it's more easy to label them. This one is, I need to look that up, that's B. Bottom is B. Not B. Then we got not A, and then we got the next one is, would be cool to have this somewhere like this. And the next flag is, let me have a look, and that is OR mode. OR, and the next one is flood carry, and then comes CN. I just name this +1 because it's smaller. And now I'm gonna put this, and then it continues with the branching. Okay. This is the branch address. So this is okay, this is kind of gonna go here. So there we got A equal B as first thing. AB, and then we got bigger than, and then we got smaller than. Looks like this. It's always AB, so one has to remember that. This should do the job. Exactly. Well, anyway, it's a better way than nothing. So, oh, this is a 1. I need to be careful with these because 1 will be parsed as binary 1. I don't want that. So I just put I for 1. Just notation, that's the address we want to jump to. So this would still be nothing. So if I go in terminal and execute that again, we get A, because that's 0. That's nothing at all. But the first instruction should not be nothing. What we're gonna do is we're gonna copy this over a bunch of times just to get some of these patterns done. I can just change the bits then. That's way too many. I don't have that many. So okay, we need 16 lines as far as I know. No, wait. We need actually. We go to 0, 9. This one is invalid, so it's 16 basically. So we have 0 to 16. Perfect. Okay, so that's all the binaries we have, which we want. The first thing we do for Fibonacci is we gonna save 0 into the first one. Oops. Boom, we got it. 0, first one. Where's the LSB? Okay, oh, I need to go to, I need to look this way, else I'm totally confused by this. It's not really easy to keep control over whatever happens here. LSB is on this side, so 1 there, and now we're gonna save 1 in the next instruction. Into this. Okay, so far so good. What we do in the next one is we're gonna do addition, and that is we're gonna add 1 and 2 together. And we're gonna save that in 1. Again, we're gonna do the same in here. We're gonna add 1 and 2 together, and we're gonna save that in 2. Means we're constantly switching where we're saving. So basically, that's Spanish, my friend, not German. Okay. There we go. So this is basically Fibonacci in easy. And once we're at the end, we're just gonna jump back to 0. So this would, oh actually we're gonna jump not back to 0, but we're gonna jump back to this instruction. Considering this is 0, 1, 2, so this is instruction 2, and the LSB is on this side. So, oops, we're gonna jump to instruction 2 in this instruction. Perfect. So this is gonna loop forever. Time to get the command. And there we go. So that's the command which actually contains all the bits. Get want. and have the ROM selected to use the plugin. Something like this. Okay, what we're gonna do is we're gonna use torture, define, and we're gonna define it so that it places the torches from left to right. So we're gonna go right direction, then we're gonna place the torches to the backwards position to me, and then we go up because there's no other layer. ROM addresses with 16 addresses, each 25-bit, defined, direction east. We're looking in east. Means the torches will be placed in east direction. Perfect. So let's just put the torture command there. ROM is full, can I write more bits? Well, that's fine. What it did is, it did exactly what I told it to do. As you can see, here we got the ones, it's just as in the file. We got the ones here, and we got the twos in here. Like there's the twos, and we got the 1, 2, 1, 2 over there, which is the same as the file. And somewhere over here we got 3 ones, which jumps to 2 permanently. Now we just have to actually check what the values are which we get here. I'm just gonna put something like this here, and then just replace these. And put redstone on top so that we can just see what it has there while it's running. So the problem is we missed the start of the program, so it's doing some random stuff, which is 2, 5, 8. Oh, that's actually Fibonacci. 8 plus 5 is 13. That is 13 plus... Oh god, it's too fast for me. And that's even 8-bit, I cannot think that high. Is there something like Fibonacci numbers in binary and stuff like... I just googled that. Binary Fibonacci sequence. Yeah, I found one. Oh, Stack Overflow. So I'm just gonna take that one and go here and make a new document. Put that here and just go and say find that with space and replace it with a new line. There we go. So time to reset this first. Reset is quite easy. We just remove that torch and then it jumps back to the first one, and then I place that torch back. So 1, 2, 0, 1, 3, 5, 8, and then we got whatever that is, 13 I believe, and then we got this one, perfect, and then we got this one, perfect, we got this one, perfect, and then this one. Nice. Okay, so we can tell that this one is working perfectly. The question is, what is the maximum that this one can do, like the maximum number? I believe for that there's no choice but to extend this row. First of all, where are we even? Are we in an 8-bit context? No, this is just 7 bits. We need one more. Okay, so what is that together in added? Let's have a look if world edit is able to do that. I'm just gonna try this first. Okay, no, it's actually not able to read binary. That sucks. And on the other side, this is wrong. Oh no, it's not. Like, I just need to swap these in my mind. Oh, but I can't do math. 1, 2, 3, 4. something like this. And that's another overflow here, this position. 1 1 1, and this is 1 0 0, and then we there. So that's the result in 8-bit. We can actually add this together one more time, so that will be 1 0 0 1 at the end, and then we go 1 0 after that, and 1 1 here. So that's the last number which actually is supported, because then we're going in an overflow. I will calculate the overflow too. So that's the overflow value. If we reach that one overflow, we got an overflow. The thing is, what we want to have is that the Fibonacci code stops on overflow in the best case. So first let's reset that one and check if that is the last value we are able to see before it totally starts with nonsense. There we go. 1 2 3 5 8 13 half of 42, whatever, more ever, 101 1101, whatever, 1001, okay, matches 1, oh, that's not right. Why is that one wrong? Have I failed the calculation? No, I did not. Why is that one wrong? Can I stop the clock at that instruction? 1 2 3 1 2 3. I'm confused. Let's have a look at this again. I'm just gonna let it run, and at some point I'm just gonna disable the clock and then manually clock it. Last one before is that one. 101,000. I'm getting close to there. Stop it. Damn it. I missed it. It's off. No, wait. It didn't save yet. That is still what the ALU output, so I can now check why this lamp is off. Or why my math skills suck. So that's the point. Let's first check the register values. That one is already why is that one not set? So that one is not set, so that already failed. So that's the reason why this whole thing fails. The question is, why is that one not set? Sadly I cannot undo. Like, it would be perfect to just say, okay, go one cycle back. That would be perfect for a CPU. Oh. Okay, that was a facepalm. I have no clue how that happened. Okay. That was not intentional. Sad. There we go. So, let's do it again. Have a look at the code again. It shouldn't work this time. Even this one should be right. That's why you should test your CPU. Because you don't want crap like that to happen. But hey, I would say, except that missing redstone, this is working instantly. That's good, right? I hope so. There we go. Yay, the value is correct. And bam, that value is correct. And the next one is the wrong one I calculated, which is not correct. No. Why? Okay, another thing to debug. Oh, come on. Wait, stop it. Go there. Jump over the first one. Start all over. Reset yourself. So this is Fibonacci, how it lives. Okay. Oh yeah, now I've got hours to wait. Great. I could eat a banana in that time until it reaches the highest number. Dum 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 dum. Okay, I should stop this here. Yeah. So we got this number, which is that one. So we want to go one step further to see what the output is. So I'm actually gonna put that here and grab myself some redstone block and just trigger the next cycle. There's the next cycle. In my opinion, the highest bit should be off. It's not. So I'd say this is the result, and it's not. And now is the question: why is it? Why isn't it? So we should check the previous two numbers. This one is actually 1001 and then a bunch of zeros. That is matching. Now let's check the other one. And there we go. So that is like the other one. 3 and let's see, that's 1001 at the end. And we got a 0 there and 3 ones. That is also correct. So there must be something wrong with the adder or my brain. First of all, let's check if that's the two numbers which we actually receive at this point. Look at this, you can see how that one is activated and that one is activated. It's because we have two ones here. But as you can see, the problem why this is not working is quite obvious. Can someone tell me how that happened? Cool. Do I need to understand this? Like, something went totally wrong with this. How? How? Like, I have no clue. How did that happen? What have I done wrong? Am I... What, is my... Okay, that is not really a bug. That is a whatever. What is that even supposed to be? Okay, result correct. It's raining outside. Why? How? Like, is there more of that crap in... Oh, by the way, while we're here, let's fix this properly. Is something like that happening on top of here? No, it's not. Perfect, cool, good. So this is the last number, and what you will notice if we're here at this step is the carryout is on. The carryout is on because at this point we're adding two ones together, so it's the higher one. So we got an overflow at this point. The overflow is visible here. The question is, how can we detect that overflow? Because when we see that overflow, we want to restart instead of save that number. Yeah, well, we get it here. So what if we, for example, do this? We're not doing subtraction, so that's not working. Let's try this one. Oh, that is working. We don't have 0, and we will never have 0 when we're checking for an overflow. Like, we're adding two non-negative. We're doing addition. We have two numbers which are not 0, and even if they are 0, the result would not be 0. It may be 0 though. If we get 111, 111, like if we get this type of result, that is 0. That has a carry. That's the only issue, I believe. Like, is it working? Yeah, you see, actually managed to not trigger this, which is an issue. Which really is an issue in this case. We could still rely on some really cheaty stuff that we say at this point the result may never be 0 because we're adding. We have two numbers, so the result here at this point is already 1, and at this point it's stored 1 in both of the registers, means that whatever happens here can never be 0. If that is the case, we can just say, I believe we can just do that. We get some form of result at that point, but I'm not sure about that. Wait, and if I, for example, now get 0, we know some overflow happened. Yeah, that wasn't right. If now is 0, we say it's an overflow. So we can say, okay, every other instruction we test if we get an overflow, or if the result is 0 by unintentional, what we did not expect. So that's already where you see the issue with the whole thing. We cannot detect that number, the overflow with 0. Like we can, but we cannot reliably do it, because at some point, if we do it, we may receive 0 at this point. Oh, well, what am I even talking? The problem is that at this point, no, we will never receive 0. There's no problem. Everything's cool. So what we're gonna do is we're just gonna change this to that. If this is the case, we're not gonna jump. Wait, we're not gonna jump. We're not gonna jump. Cool. But I want to jump. I want to jump if this is not the case. How do I invert that? So I want to jump when there's no... Wait, like this. Jump when there is an overflow.